Good afternoon. So it's my great pleasure to deliver a talk. It's more scientific than yesterday, and I will try to make it as simple as possible. First, let me mention my collaborators, two of them from India, Suhail and Arol, and three others from Poland. And here are, as you see, mentioned in blue, Grzegorz, who is here and who used to be my PhD student. So I will talk about mathematical problem with some military aspects. I will discuss 36 officers' problem of Euler and perhaps its quantization. Look, I decompose 2024 into 1900 plus 1 plus 11 square plus 3. I hope to explain later on. But first, let me show you a difference. You see, I brought some cards with me. So what is the main difference between chess and bridge? So chess, you know how to play chess, is a deterministic game, two players. Bridge is less deterministic. There's a probabilistic component, and there are four players. So this you know. I have here some cards. Look how big they are. I will use them soon. So you see the main difference. Then going back to quantum problems, to quantum entanglement, I will discuss correlations. But first, correlations between two subsystems, like A and B, and later correlations between, for instance, multipartite systems, like with bridge, four-partite systems, and then I can discuss correlations between, let's say, A, B, and C, D, or AC, or AD, and so on. Well, let's see if it works. Yes, okay, sorry. So let me remind you, there was a question yesterday. I discussed Bloch sphere, all pure states of a single qubit system with two levels can be represented by a point on the sphere, and they can be represented like this. It's just a superposition of 0 and 1. There was this question of yesterday, for larger dimension n, we have analogs of Bloch, call it Pn, the space of all pure states. It is, mathematically speaking, complex projective space, but it is isotropic. So all states are equal, like on the sphere. There are no states with extremal properties, so there is no structure, unless you impose some structure. So you can say that all quantum states are equal, but some of them are more equal than others. Maybe you know the quotation. If there is structure imposed. For instance, if you have two subsystems, like two aces here, so I have a composite system, and I say, I distinguish one subsystem, another subsystem, then of course you can distinguish product states. They are separable states without any correlation entanglement, or just the opposite, maximally entangled Bell-like states. You know the definition, like correlated superposition of 0, 0 plus 1, 1. And they are very much special. Bell states are special because they are the most entangled two-qubit states as possible. So in this work, we pose a question for larger systems. What are the analogs of the Bell states which display extremal properties, which are as entangled as possible? And then at the beginning, I will discuss some simple mathematics. In Poland, we have such a nice book, Śladami Pitagorasa by Szczepan Jeleński and Lilavati. And then there's a book for high school students, and there are magic squares introduced. So what is a magic square? You have here an example, like 3 times 3 square, and maybe you know the pattern. The sum in each column, each row is constant. And there's a related notion called Greco-Latin square, and it's a one-to-one relation. Having such a magic square, by such a change of variables, you had a pattern which we call Greco-Latin square in the following way. So look, alpha, beta, and gamma are Greek letters. In each column, each row, there is only once a single letter. And then capital A, B, C are Latin letters and have the same properties. And the most important fact is those states are orthogonal in the sense that there is no repetition of two symbols. It was first Euler who studied those objects, mathematical objects, and he used Latin and Greek letters, and therefore it's called Greco-Latin square. And they are classical designs used in combinatorics for combinatorial designs, and they are used and analyzed in different fields of science, like in statistics. In general, a combinatorial design is a special constellation of elements which are arranged with special symmetry and balance. So here there's special symmetry, that there is no repetition of symbols in each row and each column. And look, so here, let's make a classical example. I have 16 cards here. Let's put them here one by one. And then the object is to put them in such a way that there is no repetition of figures and of suits in each row and each column. So how do you think? Is it possible? So of course, this is not the good solution, but you understand the problem. So I should reshuffle those cards in such a way that I have, let's say, single ace in each column, each row. This is not so simple. I will not do it till the very end, but I will show you the solution. This is doable. Here it is a solution. Look, you can check. Very simple. You have 16 cards, and in each row, each column, there is only one ace, one king, one jack, and one queen. Are you with me? You understand the problem? Simple, yes?
Maybe you're going to leave it here so that everyone can try very well.
Yes, yes. It is simple, but not so simple. By the way, you can ask a natural mathematical question. For what dimensionalities such a solution is possible? Well, it's easy to see that for n equal 2, this is not possible. Why? If you have only 4 cards, 2 aces and 2 kings, you start with 2 aces. Now you take this king, and you cannot put it because you will have 2 diamonds in one row, or in a single row, or in a single column. So for n equal 2, such a solution does not exist, but it exists for, look, d equal 3, 4, and 5. It is simple to show they do exist. In fact, it exists also for other primes or power of primes, but 6 is a very special number. Why? It is the first number which is neither prime nor a power of prime. Of course, you know that 6 is 2 times 3. And the problem is, and Euler was asked to solve such a problem. He was then in St. Petersburg, and therefore it is now called 36 officers problem. The idea is simple. There are 36 officers from 6 different units of 6 different ranks, and there was a parade in front of the Tsar, Katarina the Great, and the idea was to order them in a nice way. What means nice way? There is no repetition of uniforms in each row, each column. So there was a very practical, let's say, military grant in some sense, and Euler was first to show that such a solution does not exist, which was very breaking, strange observation, because for 25 officers it was possible, for 16 and 9 also, and for 36 it was not. But even Euler himself was not able to prove such a simple fact. He only conjectured that it is not possible. And the proof was given only 121, so look, 11 square, years later by a French, not mathematician even, lawyer, Gaston Tarry. And then another story says that it was the last important result in mathematics obtained by not a professional. He was sent to Algeria and perhaps as a civil servant and had nothing better to do. But his achievement was great because he showed that it was possible to reduce like several millions of possible cases into a few thousands, and then show one by one that out of those few thousands, there is no solution, which was basically very much non-trivial. So even Poincaré was very much amazed by his result. Wow. So I started with bridge and chess. Let me go now back to chess. So, you know, it's a very simple problem. We want to put 6 rocks in such a way that they do not attack each other. So this is a simple solution. You see they are put in such a way no chess attacks each other. This is the first step to study this problem. Now look, it's more complicated. I use now 6 times 6 different figures, but let's assume they still have the same rules like chess. So now look, if you take, for instance, pawns, in each row, each column, there's only a single pawn. So if pawns were rocks, there were no other figures, they do not attack each other. So this is simple, but from the Euler point of view, this is just a single Latin square of order 6, yes? Are you with me? To get the full solution of the Euler problem, we have to go one step further. We have to color them, so pick 6 colors. and to color them in such a way. So look, this is the same solution, black and white. Now I choose 6 colors. It's exactly the same pattern. And I start to color them in such a way that in each row, each column, there's only a single color. So you see, I'm almost done. There are only 4 pieces left. And I have 4 colors, 2 cyan, 2 green. So I'm almost done. And this is the point. So it looks like the solution is possible. However, in some sense, it's like 2 times 2 problem. Now it's easy to show that for this particular starting of 32 cards of pieces, this solution does not exist. So this is easy to check that taking those 4 pieces and taking 2 colors left, you cannot obey the rules. It will be the case that in some rows or columns, 2 colors will be repeated. And this is the classical problem. We will slowly go to a quantum case. I only emphasize that this French guy, Tari, was the first to show, strictly give a rigorous proof that Euler was right in this aspect. There is no classical solution of the famous problem of 36 officers. By the way, I managed to see such a nice game. It is a game for, well, clever kids, which is very simple. But look, it is more or less the problem of Euler. Because as you can guess, you put those pieces apart and the task is to arrange them in such a way. Now look, in each row, each column, there is only 1 color. It corresponds, let's say, to different units of the officers. And concerning rank, you have 1, 2, 3, 4, 5, 6. There are heights of different kind. So now it's a question. So maybe Euler was wrong, because this looks like apparently a solution. And I think this is a nice difference between physics and mathematics. Of course, Euler was correct. There's no solution exists. And what is this? How do you can guess? So Mike, I will ask you, what is your opinion? Is it a solution or not? It's a physical approximation to the solution. There is a trick inside and nobody sees it. Basically, the trick is that all pieces are done correctly, but 2 pieces here, they look to be of rank 5, but somehow inside there is something special that they play the role of rank 4. So therefore, it's not exact solution, but it looks like a solution. Yeah. So in some sense, a fake solution. Yeah. Okay, but fake solution maybe is too strong. It's an approximating solution. In a sense, it is similar to this solution here. So 4 pieces are somehow not correct. Okay, and now we go to quantum. So what is the change? Instead of numbers 1, 2, 3, 4, 5, I have states. And here we have I will quote an important paper, by the way, written in German. It was a thesis. So I will wish all young people who are planning to prepare thesis in quantum or in theoretical physics to produce such a thesis like this one, because it was really an influential paper. A few years after he defended his thesis, he was asked even to translate it into English. Now there is a paper in English, basically translated the thesis because it was so influential. So the title is something like Grundzüge einer nicht-kommutativer Designtheorie. So it means the basics of the quantum theory of designs. So the idea is simple. This is Sudoku. You know what is Sudoku, but it's simpler for beginners. 4 times 4 Sudoku. In each row, each column, you have different colors are here not important. Different numbers. Also in each block, they are different. So it is a special pattern of Latin square. And here's our quantized version. We also had a paper on this. So what is the difference? Instead of numbers 1, 2, 3, 4, I have states 1, 2, 3, 4. But here classically we say, they are different. Okay, we know what it means that the numbers are different. What is the difference in quantum mechanics? They are distinguishable. So they are orthogonal. So instead of being different in the quantum setup, for quantum designs, we have orthogonal bases. So all states are orthogonal. So this is like a trivial example. We just put the same solution of Sudoku and decorated by cats. But now look, here is more complicated. And now it's a really quantum Sudoku, because you have like states which are really orthogonal. In each column, each row, in each block, you have orthogonal basis. So in some sense, here is more complicated case. From physical perspective, it's a collection of Lüders von Neumann orthogonal measurements. So you have 16 states such that in each rows, each columns, each blocks, they correspond to orthogonal measurements. And in short, going from classical to quantum increases the space of solutions. Here we have some nice quantum solutions which are not doable classic. So of course, in blue, Grzegorz was also co-author of this paper. And now we will go to quantum analog of Euler problem. But then, well, so again, here we have like, instead of classical Latin square, we have quantum Latin square. So here 1, 2, 3, 4 are 4 states, but now I can use some linear superposition of states. They can be like superpositions. Here is example I quote from the paper by Vicari and Musto, which was also important, influential. I think they were the first to study such problems. So this is a quantization of a single Latin square. Now I will go to quantization of 2 orthogonal Latin square. For instance, this pattern with 9 cards, not 16 by 9. So what this means ace of, well, let's say king of spades. You know how it looks like. But for me, there are 2 quantum numbers, king and spades. So in some sense, they are product states, king times spades. So any classical solution can be represented like this, where here this means a product state. Now to go to another class of solutions, instead of those product states in each box, I can allow, according to the rules of quantum theory, to put the superposition of states or even entangled states. So without going here into technical details, I will only mention one thing. For composed systems, we know separable states without correlations and entangled states with correlations, like those Bell states. They are maximally entangled because technically some entropy of entanglement, which can be defined precisely, is maximal. Entropy is maximal. It means you have no knowledge about the state. Large entropy means large uncertainty about the outcome of measurements. And then absolutely maximally entangled states, if you have 2 subsystems, let's say 2 aces, we know what is maximally entangled, Bell state. Now let's assume we have 4 cards. Could you hold those 2 for me? What means entangled? You can now consider, like in bridge, entanglement between those 2 cards and those 2 cards. And absolutely maximally entangled means that we have maximal entanglement for such a partition. But also, a bit slower. Yes, okay. If we now make a flip exchange 2 cards, it should be also maximally entangled. And for last case, we assume absolutely maximally entangled means, you see, we play cards here, that the entanglement is maximal, irrespectively how you split the system of 4 cards in 2 pairs. Is it clear to you? So in a sense, there are more constraints because we assume maximal entanglement for such a splitting and all possible other splittings. And this is simplest to define for 4 cards. Okay, and then, okay, I should also quote some other papers, and it's related to some tensor theory, and many people work on this. If you wish, I will give you the presentation, which includes reference to all details, but here we have to proceed. And then in short, there is a, okay, theorem is, there is a relation between 2 seemingly different problems. If you find solution of the quantum version of the problem of Euler, what is quantum version? You allow for entangled states in each box, then you will find equivalent absolutely maximally entangled state of 4 subsystems with d levels each. So this is relatively simple to show that there is a relation between those 2 problems. And now we can here show that some people studied this problem of existence of those absolutely maximally entangled states. So here we have D is number of levels in each subsystem, N is number of systems. So we know that there are no absolutely maximally entangled states of 4 qubits. Green means such a state exists, red does not exist, and white was the first white spot. So nobody knew whether such a solution for 4 Q hex exists. And well, those solutions are related to quantum error correction codes. And here is some technical details how we were looking for the solution. Here is a picture of Krakow with some optical effects, but I have to speed up. So I will not going to discuss now today how we obtain the solution, but here it is a solution. So look, what you see is a 6x6 board, but instead of having a single officer, we are joking it's an entangled officer, because we have a superposition of 2 chess or 3 or 4 chess figures. But what you see in the first glance, the colors are how split it in some sense uniformly. The average color in each column, each in a row is white. White means it's average out. Also, average rank of the piece of chess piece or of the officer is also white in a sense. They are all in each column, each row, they appear with the same probability. Basically, the size of each figure corresponds to amplitude. The larger figures, so here are like Bell states composed of two figures. And one important assumption is that all those boxes, we have one should assume the states are orthogonal, they are different. But now look, you can say, I'm wrong. Look here, you have a pink horse, a knight, and the white pawn. Or maybe here it's something wrong. Okay, because I forgot to add phases. We have possibility to add complex phases. And the full solution looks like this. So a part of the same pattern, we also add complex phases, which happen to be multiple of root of identity of rank 20. Why 20? This was found by analytically at the very end by solving some equations. So this is the full solution of the problem, which looks perhaps strange, but here it is another version. So this is the first state, which in the standard notation looks like this, and in the chess notation looks like this, a superposition of 2 or 3 of chess figures where ABC are constants, which we know they are very simple, and omega is just the root of identity of size 20. Okay, so not going now into details, here's another version of the same pattern. Here's how we were working on this. So basically, we got numerically a huge matrix of size 36. We rearranged it once, then we arranged it another time to have a form of 9 blocks of size 4. Since it has to be unitary, we wrote unitarity conditions in each block, solve them analytically, and got the solution. Okay, so there are different ways to represent this solution. Now we call it a quantum version of the problem of Euler, which has a positive solution. And now another remark. It is related to this absolutely maximally entangled state of 4 subsystems with 6 levels each. So they're exactly like 4 dice. I was showing 4 dice yesterday. So the idea is like this. If you have 4 dice and you prepare them in such a state, now you pick 2 dice out of those 4, like red and black. You measure them and you can predict the outcome obtained on the other 2 dice. And this is the case irrespectively which 2 dice you choose. If you choose blue and red, you can then infer results on green and black and so on. Well, now we can ask at the very end. We found a nice solution of a nice state for 4 dice problem, 4 subsystems, quantum subsystems with 6 levels each. But of course, a critical person can ask, why do we care? Why we look for such states? And now look at the simple picture. This is like C is something classical, Q is something quantum. And this picture can show, for instance, the space of classical and quantum states, but also space of classical quantum operations or correlations, and maybe protocols and algorithms, or maybe even technologies. So now here we found such an object with extremal properties, which is as far as possible from the set of classical states. So in some sense, it gives us the advantage. What is quantum advantage? It's a difference between the optimum over all possible quantum solutions of the problem to the classical. So now we hope that such an example shows that this is only, in the first case, we found a nice example of advantage concerning quantum states. But we hope it will be related to other more practical issues, finding optimal quantum operation, or even quantum protocols or quantum technologies. I'm almost about to finish. So here are my concluding remarks, that we found that there exist strongly entangled extremal states of 4-dice problem, which is related to the famous problem of 36 officers of Euler. And finding such object has a lot of more or less practical implications concerning existence of some objects called perfect tensors, but also finding new quantum error correction code, which allows to encode, in short, one dice, so object with 6 levels, into 3 dice, in such a way that if error happens on one of those 3 dice, one can recover the information. I'm almost done, but I will mention relation to our paper, which was at the archive in 22. So you see, this is like, okay, entangled officers, because instead of a single card, I allow for superposition of 2 cards. So I will quote from our paper, where we have written like this. It is sad to note that these Russian officers recently left the parade ground in St. Petersburg, where they belong, and went 1,000 miles south. However, explicit analytical results described in this work strongly suggest that the officers might eventually suffer a transition to a highly entangled state. Thank you very much.
Thanks a lot for a very entertaining talk and such a positive remark at the end. Since entangled state, as far as I understand, is some psychic state which does not allow you to perform military operations, which would be definitely what we...
Even more, in medicine, entangled state of the mind is some concrete remark used by people working in psychiatry and medicine, which is not a positive statement.
Well, positive, no, not for them, definitely.
Yeah, for the patients, yeah.
Anyway, another thing that you can observe from your talk is that you can play with cards at the university and still get paid, which is
Legally, yes, legally.
Legally. Okay. Please.
So first of all, thank you very much for very interesting talk. May I ask you if it is possible to put your problem, for instance, on a sphere, on a torus, because you consider on a plane, but when you have some another
geometry,
topology, is a torus or sphere?
Okay, let me think. In a sense, we have 4 times 4 square. It is a square. So usually you can associate square with a torus.
Periodic.
Yes, yes. But here, in fact, there are no periodic conditions yet. But in a sense, the only rules are there are different cards in each row, each column, which in a sense is like torus, like object. Yes. Because we don't care about boundaries. Boundaries are not important. However, concerning sphere, so here we have a square. So in a sense, like toric quantization. But look, it could be nice to look for a kind of analogy concerning classical combinatorial objects related to the sphere. Here, those objects were related to the square, which corresponds to a torus. But on the other hand, this is a square, but there are also combinatorial objects called cubes. They are Latin cubes, like a hypercubes. So it will be correspond to torus in not two-dimensional, but 3 or 4-dimensional. This can be done. Thank you very much.
Thank you.
Yeah, thank you very much also for this very interesting talk. I have a bit naive maybe question, but I understood, so far I understood, entanglement is a resource for
Yes,
these
yes.
things. Yeah, this is what we can call the quantum, and this is clearly, it's necessary to have entanglement in order to solve this problem in this case. But my question, is it sufficient to have entanglement?
Well, it depends to what, but your question is very nice in the sense that if you have Bell state, like between two cards, two objects, you can perform the famous teleportation protocol I discussed yesterday. And now if you have, again, let me take 4 cards here, please hold them. So with our state, we can perform teleportation of 2 dices from A, B to C, D, but also if we exchange cards, we can do it from A, C to B, D, and so on. So our solution, the solution, quantum solution of the problem of Euler and our absolutely maximally entangled state allows for such a teleportation protocol, which was not possible with standard state of GHZ.
Okay, so
So
there
it
is
exactly is applied.
substate,
Yes.
yeah. Okay,
Yes.
thank you very
Yes.
much.
And I think there is also an online question from Malik. So please.
Yes, thank you, Professor, for the talk. It was very nice. Me particularly, since 2 weeks, I'm doing a master on this on your article that you have published on this 36 Euler official problem. So it was a great pleasure for me to assist this talk.
Thank you.
Then my question is about one of the open question you are asking in one of your articles. 9 times 4 equals 6 times 6, understanding the 36 Euler official problem. This year, in that article, after presenting the solution that you were presenting here, you asked one of the open questions you are asking is, does the real solution of the 36 Euler official problem exist? In other terms, does the Hadamard matrix of that problem exist? And in 2024, this year, in January 2024, this year, you published an article titled complex Hadamard matrix of size 36. Complex true unitary Hadamard matrix, yes. Complex true unitary Hadamard matrix. So my question is, for you, since you have experience on that domain, for you, does the real Hadamard matrix exist really? Is it the problem of construction of the real Hadamard matrix, which is a problem now, or is it the problem of existence of this of that matrix?
Thank you for the question. I'm very much impressed how much you already learned and how much you know. Indeed, the situation was like this. First, we found this solution with 36 officers of Euler. Then with other colleagues, we found the solution in terms of the complex Hadamard matrix of size 36. And this is done. However, the question which is open whether such a matrix exists for the real Hadamard matrices. And here we do not know the answer. So this is still an open question. I would love to know the answer if such a solution exists, because it would be even simpler solution. Even simpler in sense of phases. Here we use 20 phases, in other solutions 6 phases. If you had real Hadamard matrix, you have only 2 signs, plus or minus. Such a solution would be simpler. I don't know whether it exists.
Okay, thank you very much, Prof.
Merci beaucoup.
Merci beaucoup, Professor.
So thanks a lot once again.